Hi there. Today we are going to introduce second-order circuits and look at their time domain response. Now, second-order circuits are circuits that have two storage components, for example, an inductor and a capacitor. And they turn out to be second-order circuits, and we call them as such because of the way the equations turn out. I'm Vivek Subramanian.
I'm Michelle Maharbis. Let's get started. So exactly what Vivek just said is what we're going to work on. Just to state it out from the beginning, a second-order circuit is going to be characterized by a second-order differential equation. We'll get into that in a minute. But just from the view of a circuit topology, you can see this will arise whenever we have two energy storage components which can't be trivially combined. So the bottom two are what we usually use as canonical examples. For example, as a resistor, an L and a C. All three of these things can't be combined with each other in any meaningful way. Same with a parallel. But it also turns out you can get second order behavior when you have, for example, two caps that can't be, I can't take C1 and C2 and add them together to make some equivalent capacitor because of this resistor.
I got it, because they're not truly in parallel with each other because there's that resistor in between.
Yeah, and so there's a number of circuits you can imagine that will give you second order behavior. We're going to focus in on one today just to walk through the solution, essentially the general solution scheme. However, we're going to be doing the same thing we've done with first order circuits in the time domain, and in fact, pretty much everything in this class. We're really just going to be looking for voltages and currents. In this case, of course, it's in the time domain, so we're solving for voltages and currents as a function of time. And where in the first order case, we were using the initial and final values of the voltage and current of interest to arrive at our solution, we are going to use that, and in addition, the derivatives of these things will be needed. Effectively, if you think about it, with a second order differential equation, I have to integrate twice, and so I need boundary conditions for the variable and boundary conditions for the derivative of the variable in order to integrate. That's pretty much what it boils down to.
And so since you're going to have two derivatives, I guess that's why it's second order, because when you put it together, you'll get a second order differential equation?
Exactly. You'll see that the derivative equations that you're used to for the inductor and the capacitor will essentially combine and give you second derivatives.
Okay, so that makes sense. Now let's go ahead and first, at a high level, look at how we would solve a time domain problem. So let's state some of the things that you already know. You know that capacitors resist abrupt changes in voltage and inductors resist abrupt changes in current. What that means is the voltage in the capacitor and the current in the inductor cannot change instantaneously.
Okay, I remember that.
That's the first point. You also know that there are relationships between the current through a capacitor and the voltage across it. Specifically, you know that the relationship that we get is related to the rate of change of voltage, right, for a capacitor. And correspondingly, the voltage across an inductor depends on the rate of change of current.
Oh, I think I know where you're going. So you're saying if I have, say, I of C, the current through a capacitor, I immediately know the derivative of the voltage of the capacitor.
Exactly, and correspondingly, if you have the derivative of the current, you know the voltage on an inductor.
Got it.
Okay? So those are two things we're going to use, and we'll sort of put them together to figure out how the circuit responds using KVLs or KCLs or what have you. Okay? So that's why you remember previously, Michelle, you said we need the voltages and their derivatives. Well, now you see why.
Right.
Okay? All right. Now, of course, to get started, we need certain pieces of information to go from steady state to the transient response and vice versa. And remember, what we take advantage of is certain behaviors, and specifically capacitors are open in DC and inductors are shorts in DC. Now, let me ask you a question, Michelle.
Do it.
Consider a transient circuit where we've got some initial condition, we flip a switch, and then we wait till infinity. Where are the DC cases applicable? In other words, what are the time invariant portions?
Okay, so assuming that we waited for all of infinity prior to t equals 0, in other words, from minus infinity to 0, and we don't have any sinusoidally oscillating inputs, then right at t equals 0, when our whatever magic we're going to do occurs, the capacitors have been sitting there forever, so they look like opens, and the inductors look like shorts.
Yeah, so that is what the time point we've been calling 0 minus.
Got it.
So one condition that we calculate as a steady state behavior is at time point 0 minus.
Okay, so that's the first one.
First one.
And using this short capacitors are open and inductors are shorts, we can get these initial conditions we're talking about.
Exactly.
And then if we wait a really long time out at t equals positive infinity and let the system settle, get any transients out, and again, if there's no sinusoidal forcing functions, it'll eventually do the same thing. It'll settle to some DC value, which means that the caps will go back to being opens and the inductors will go back to being shorts.
So what you have is you have two time points for which you can use time invariant analysis. Specifically, you have so steady state analysis can be done at time is equal to 0 minus and at time is equal to infinity.
And we did this for the first order circuit.
Exactly. We did it for the first order circuits. And remember, the reason we got to do this is we assume that the circuit has been sitting in its pre-switching state long enough to have reached steady state for 0 minus. And correspondingly, the transient is long done by the time you reach infinity.
Cool.
All right, so we've set that up, Michelle. Maybe we can use this information to start setting up how we're going to deal with these problems.
Okay, and the example we're going to do is an RLC series. So it's basically a resistor in series with an inductor in series with a capacitor. And we're going to be interested in solving for the voltage on the capacitor. And we're doing this just to pick something and go through a canonical example. At the end, we'll tabulate it for a parallel RLC.
Hey, but let me guess. If we are doing it for the voltage across a capacitor, I can find the current through that capacitor, and that current through the capacitor, because they're all in series, would be the current through the inductor, etc.
Exactly.
Got it.
So once you know this, you can use the equations you know to arrive at the current. Great. Now, the way we're going to set it up is we're going to pre-charge the whole circuit using a DC source Vs, which has been sitting there for all of time prior to t equals 0. And then at t equals 0, we're going to flip the switch.
Got it.
And when we do, we're going to have, as you can just see by observation, we're going to be left with this circuit down here, and we'll talk through that in a minute.
Okay, but I'm looking at that circuit, at the one down here, and there is no voltage source connected in. So that would be a natural response as we've defined it earlier.
That's exactly right. So what we're going to be solving for is the natural response of a series RLC. In other words, if you charge it up and then let it go, what does it do naturally with no forcing function? So let's just go through the boundary conditions for this, right? If I pre-charge, in the case where the switch hasn't been flipped yet, it's only connected to 1.
Yep.
Right? We know what about the capacitor?
Well, because the capacitor will behave as an open, it'll charge up to the voltage of the source.
Exactly.
So at time is equal to 0 minus, the voltage across the capacitor should exactly equal to Vs. And that's for two reasons. One is the inductor behaves like a short, and two is the capacitor behaves like an open. And just the fact that the capacitor behaves like an open is sufficient to tell me that the voltage across that capacitor at time is equal to 0 minus will be the source voltage Vs.
Okay, so following that train of thought, once I flip the switch, this switch has changed. Does the capacitor voltage change to something different instantaneously?
The instantaneous voltage, because we've said that capacitors do not like abrupt changes in voltage, the instantaneous voltage would be the same.
Right. And so here's our first initial condition. We know the value of the natural response of the voltage on the capacitor. We know it to be Vs by this sort of two-part trick we just did.
Got it. And that's what we had done in the first order circuits
exactly.
as well.
We're just doing exactly what we did before, just refreshing. Now we know something else. What is the current through the inductor?
Well, because the capacitor is an open, there's going to be no current flow at time is equal to 0 minus.
There you go.
Okay.
And we know that at t0 minus, can the current through an inductor change instantaneously?
No. Inductors resist abrupt changes in current, so at time is equal to 0, the current through the inductor should be 0. Oh, cool. So I've got two starting conditions for my analysis.
So let's cheat. We're jumping a slide ahead. But if I know that I equals C dV dt for this cap, and I know that this I must be that I, don't I know dV dt for the capacitor as well?
Oh, yeah. Okay. Yeah, things are starting to... Okay, I get it.
We'll get back to that.
So we're taking advantage of both of these to sort of figure out the overall response.
Exactly. Okay. So now, looking at the natural circuit, or the natural response of this circuit, so looking at this circuit at t greater than 0, we can do a KVL.
Yep. Okay, I got it. And it's because there's no source in there, it's just going to be the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor is equal to 0.
Perfect.
Aha. And so that's Ri from Ohm's law for the resistor. It's L di dt for the inductor. And the voltage across the capacitor is just the voltage V.
Right, that's our variable.
Okay.
We could have called it V sub C.
Got it.
We were just calling it
And the
V.
sum of those is 0.
Right. Now, we also know that the current through the capacitor is the same as the current through the inductor.
Yeah, by current continuity.
Yep.
Okay.
And that equals C dV dt.
Got it.
So substituting in,
Aha.
cleaning
Okay.
out so that...
So anytime we have an I, I'm replacing it by C dV dt.
Right.
So in the so the Ri gets replaced by R C dV dt, and the L di dt gets replaced by L C d square V dt square.
Perfect.
Got it.
And so what we're going to do is we're going to divide out, by this LC and so on, just so that we clean it out. Usually the standard form, we like to have the highest derivative not have a coefficient or have a coefficient of 1. So you clean it out. And this is the standard form. And so that, double dots or double dashes kind of indicate second derivative. So with time. So here's the form, right?
Okay. So you've just rearranged it by dividing everything out. And and we write it in a standard form of V double prime plus A V prime plus BV is equal to C. For that to be true for this equation up here, A would have to be R over L, B would have to be 1 over LC, and C would be 0 because it's on the right-hand side.
Right. Now, in general, if there were forcing sources, this C would have some value other than 0, but
Right.
because it's 0...
That's because this over here would not be 0 if there was a source.
Exactly,
Got it.
just by KVL. Okay. So now we've got ourselves an equation.
Okay.
Now we've got to solve the second order differential equation. What
All
do we
right.
do now?
Well, let's go ahead. I assume what we're going to do, and obviously I assume it because I'm about to do it, is I assume that we will have to use a standard form. Okay? So let's go ahead and set that up. Okay, so to start, we'll go ahead and take that form of the differential equation that we had, which is this one right over here. And I'm going to make an important assumption. I'm trying to calculate the voltage, right? That's when I solve this equation, I'm finding the voltage.
You're solving for V of t.
I'm solving for V of t, exactly, the time-dependent voltage. I'm going to make an important assumption. I'm going to assume that whatever solution I get, I'm going to be able to represent as this form. V of t is going to take a form of some exponential A exponential of s times t.
Why of all the things on earth would you pick that?
Well, I'll give you the answer in two ways.
Okay.
First, mathematically, dealing with exponentials is nice because the integration is straightforward.
Oh, I see. Derivatives
Okay.
of exponentials are exponential.
Right. Integration and differentiation is straightforward, so that's nice. So at least mathematically, that's a good starting point.
Okay.
Okay.
Not a very good reason.
Well, we like easy math, right? Okay. But the second reason, which turns out to be more technically relevant, is at this point, you've hopefully covered phasors, right? I mean, you've seen our phasor videos. And think about it. With an exponential, if I have a real part to if s is real,
Then it's,
I can show rises or falls.
oh,
depending-
right. If it's e to the minus something t, it's a decaying
it's a decaying
exponential.
function.
E to the plus something t is
a rising
blowing up.
form.
But then, wait, so this thing must only blow up and decay? That doesn't make any
well,
sense.
no. Think about it this way. What if, given what you've learned about phasors, what if s was imaginary?
Aha!
I can
So if you
also
had an
represent sinusoids.
So I get it. So e to the st is pretty powerful, right?
Yes. Now, we're still making an assumption at this point that the solution that we're going to get
Right.
is either an exponential decay, an exponential rise, or a sinusoid, but that's not bad, right?
That isn't bad. It does
Yeah.
capture what you intrinsically... So it's a good guess.
Right, and think about it this way. When we did the first order circuits, we saw that those switched response were usually exponential decays or rises, depending on whether we were charging or discharging.
Oh,
And when we did phasors, we said, well, we get this oscillating behavior when we have inductors and capacitors. So this seems to be a good case to cover all cases.
All right, let's try.
Okay, so let's try that. And of course, the fundamental point is the math is easy, so we like these.
Right.
Okay? All right. Now, if this is our solution, we can, of course, plug this back into here, take the first and second derivatives, and we should get the full form.
Okay.
Right? And this is where the exponential is mathematically very powerful because, as you said earlier, the derivative of an exponential is based on the exponential itself, so this is what that solution ends up being.
Easy.
Okay.
Oh, and then all these a's
And
are
all the a, e to the st's
Aha.
cancel out, and we get a quadratic.
So wait a minute. So, okay, so once I do this, I can solve for s.
Right.
Well, I want to know what that is.
Right, because I have a quadratic, which I can solve for just using standard quadratic formulations. And standard quadratic formulations, you know, when you have a quadratic, it takes this form, right? You have the negative and positive half roots.
Okay, but that means that for an arbitrary solution, I'm going to have two s's, an s1 and an s2. But
Correct. That's right.
Okay, so
Okay.
then how do I
Well,
kind of modify my...
Well, remember, this is what the roots are. So then if you were to write the overall function will just be calculated as the combination of those two, and that's this form right over here.
Aha, but oh, I get it. So then that's s1 is up there, s2 is
Yep.
here, and a1 and a2 are things where I guess we're going to have to solve for.
Correct. And take a guess as to how we're going to solve for those.
Well, the only other information that I know for sure are the initial conditions.
Right. So I will figure out A1 and A2 based on the initial conditions.
Okay.
And then I'll do that. So maybe you can do that. Start setting this up, Michelle.
Maybe I can. Let's try this out. All right. So we've got this equation. We know how to arrive at S1 and S2 from A and B, which we got from our circuit. That just comes
right.
from our
And as a reminder, A and B are calculated from the resistance, inductance, and capacitance, because those were defined in the standard form.
So we're pretty comfortable with those. Now we've got to figure out A1 and A2.
Right.
All right. Well, there we go. That's the form of the solution. And to remind everybody, we went through this a minute ago, but you know the initial voltage on the capacitor,
and
right?
the initial current on the inductor.
And the initial current on the inductor. So let's use those two little tricks. First of all, to summarize in writing, I know V at t equals 0, right?
Right.
Because it equals V at 0 minus, because of the non-instantaneous change in voltage on a cap, equals Vs.
Yeah, and that's because the capacitor was initially charged to Vs,
Perfect.
and correspondingly the inductor current was initially 0.
Perfect.
Got it.
Now, and this is the thing we sort of jumped ahead a little earlier, but because I know that the current through the capacitor is C dV dt, and I know the current through the capacitor, and I know this because it's the same as the current through the inductor, and the inductor current can't change instantaneously. So that's the only reason this works. It's both things have to be true. The inductor refuses to change instantaneously, which forces the current through the capacitor to be the same as itself.
Yes.
So because that's true, I know the derivative. I know dV dt, because
Yep.
dV dt is just 1 over C
Right.
I at 0.
But because the inductor current is 0, that's just going to be
It
0.
just in this case, it turns out to be
Yep,
trivial
got
at
it.
0.
Mhm.
Okay, so now we know V at 0, and we know dV dt at 0, or V prime at 0.
Yep.
Those are the two boundary conditions
yep.
we're going to use. Okay, so then all we do is say, well, if I put a 0 here, V at 0 equals A1 e to the S1 0 plus
Yep.
A2 e to the S2 0, which, of course, that's going to go to
Right, but
1.
we know the initial voltage is just Vs, because
right.
that's what it was at time 0.
That's what we have right here. That's our first
Okay.
initial condition.
Okay.
So now we've got an equation. I don't know what to do with it yet. Let's just kind of write it on the corner somewhere. Okay, now the derivative of this we can take, just the generic
Sure.
terms, right? It's S1 A1 e to the S1t plus S2 A2 e to the
Woohoo! Exponentials again!
You're right, actually. It
Okay.
turned out I was making fun of you, but you're right. And at t equals 0, you put zeros in there. Again, these things go to 1s. And now in this case, we know this. We know the derivative is 0.
Is 0.
So
Aha.
now I know this expression equals 0.
Okay, I've got it. Now we've got two equations with two unknowns.
There's the second equation.
Aha, and so we can solve them for A1 and A2.
That's right. So from the value of the variable at t equals 0 and the value of the derivative of that variable t equals 0, we had two equations.
Got it.
Right? One here, one here. Take these two,
Solve
them. You can solve for the value of A1 and A2.
Okay, now hold up. Let me see. So S1 and S2, I know because they come from the roots.
Mm-hmm.
They had within them the A, B, and C, which were in turn calculated from the resistor value,
Mm-hmm.
the inductor value, and the capacitor value.
That's right. So these you know
Aha.
from those values.
Okay.
And then we can put them back into the original expression, right? Since we now have
Yeah.
expressions for them. Clean it up a little bit because you can tell, see, this is just it's fairly similar to this, has the same denominator, so
yeah.
we can clean it up a little bit. And we are left with this general expression. Now here's the trick, and this is the part that maybe you can walk us through. That we've got to go back and do a little thinking about these roots, because these roots can take on different forms depending on how big some values in your circuit are, and that'll lead to different circuit behavior.
And that makes sense because you told me, well, we discussed earlier that the whole reason we set these things up as exponentials is so that they can describe both exponentials and phasor-like responses, in other words, oscillating
Exactly.
responses.
So now we've got to go back and look at S1 and see if
Aha.
it's real or
All right,
imaginary.
because if it's real, it'll do one thing, it'll be an
Right.
exponential, whereas if it has an imaginary part, there's going to be some oscillation to it.
Right. So the bottom line of this, up to this point, is we've given you a procedure for solving for these A1s and A2s. In the subsequent slides, as we go through different cases, we might call them B1 and B2 and so on to distinguish different cases. But the general procedure is exactly what we've outlined.
Okay. All right, let's go ahead and do that. So what we're going to introduce is something that defines how the behavior looks as a function of what these roots look like.
Okay.
Specifically, we're going to look at whether these roots are real or whether they are complex.
Okay.
And you can probably already guess, if they're real, they're going to be exponentials without any oscillation. If they're complex, because of Euler's formula, we get sinusoids and cosines, and so we should see some sort of oscillating behavior. Now we're going to define those. Okay? And remember, as a reminder, these are what we calculated the roots to be. So this is my S1 equation, and this is my S2 equation. Just to clean it up and get rid of the fact that we're dividing by 2, I can write them in this form. Instead of writing it as A and B, I'm just going to write it as alpha and omega. Now, I haven't told you why I'm calling them alpha and omega. Hold that thought for a second.
Dun, dun.
All right? Hold that. Now, so this is just sort of symbolic representation. You can obviously figure out what alpha and omega are, and specifically what you find is alpha is just A over 2, and omega is just square root of B.
Okay. Can I make some observations?
Not yet.
All right.
Okay. Before you make the observation, of course, we know what A and B are because we defined those originally.
That's right.
Right?
So R over L.
And so we know that since A was just R over L, alpha is R over 2L, and correspondingly, omega naught is 1 over square root of LC. Now make your brilliant observations.
Drum roll, please. Okay, so while you were talking, not to imply that I don't listen to you when you're talking, but while you were talking, I was staring at these things, and I noticed something. So this S1 is always, it has this minus alpha is always going to be minus and real.
Oh, but let's think about it. Yeah, that makes sense because R and L are both positive numbers,
Right.
so minus alpha will always be a net negative number.
Right. So now let's ignore everything over here. So if
Okay.
it was just this, then these guys would just be decaying exponentially.
Aha. Oh, no, I get it. Okay, because, so we ignore everything in the square root. So we've just got S1 is minus alpha.
Right.
And S2 is minus alpha for that matter.
Right.
Okay? And because it goes into this exponential over here, these will be decaying exponentials.
Right.
Cool. Okay. And I get it, and that's why you call it a damping coefficient, because it shows how the function decays away.
Right. Now, in the real expression, that was just sort of hypothetical. We can't ignore this. There's obviously something there. But I also noticed that depending on which is bigger, alpha or omega, the thing under the square root is going to be a negative number or a positive number.
Right.
Right?
Right.
Because these are squares.
So that part in there describes whether you're going to get a complex number or a purely real number.
Exactly. So if it's a real number, it'll just be some negative number, minus alpha plus or minus some number. So
Yeah.
it'll just be kind of like minus alpha. Still decaying, but not quite as much, depending.
Right. And by the way, it has to be decaying because remember, this is square root of alpha square minus omega square, which means what's in here can never be larger than alpha.
Right.
So you're always going to end up with a decaying function.
Right. But the interesting thing is when alpha squared is greater than omega, less than, you'll get a negative number.
Yep, got it.
Got it. Okay, so my guess is that we've got at least two conditions just comparing alpha to omega
Yes,
squared.
you're right. Okay, we're going to have a condition that comes out of the fact comes when it's purely real. Okay, we're going to have a condition that shows up when we have a complex number, and there's going to be a kind of interesting boundary case that we'll look at. Okay?
Oh, when they're equal to each other.
Yep. Okay.
Okay,
so
let's do that.
let's consider the case where alpha is greater than omega. Okay, when alpha is greater than omega, what happens to what's in the square root?
So that's going to be real.
Yep, it's positive. So that means the square root is purely real, which means S1 and S2 are real.
Got it.
Okay? In that case, take an exponential with a purely real number. What is it? It's an exponential decaying function.
Right.
Right?
Real and negative, yeah.
Real and negative because it's minus alpha.
Got it. So
Okay?
basically in that case it's just going to die down.
Yeah, and we call that the overdamped response because
Okay.
it dies down. Okay?
Okay.
Let's consider the case where alpha is less than omega. Then what happens to the square root form?
Oh, so you get a negative number, so you're going to have it's going to have to be complex. Square
Yep.
root of a negative number is a
Right.
complex.
This is complex, and now just jumping ahead a little.
Oh, wait. Ooh.
Okay.
That means you have e to the minus real number plus j something, which means there must be a sinusoid in there somewhere.
Yes.
Aha.
Euler, based on the stuff you hopefully remember from phasors, we will have some sort of oscillating behavior because Euler's equation or Euler's identity tells you a sinusoid that the exponential of a complex number can be represented as a sum of a sine and a cosine.
Yeah, that's
Okay.
pretty cool.
All right. So we call that the underdamped response. And the reason is, as you're going to see, it doesn't just decay out. It sort of bumps around a little before it dies out.
Oh, it oscillates
Okay?
a bit.
Yeah, it oscillates a bit.
Okay.
All right. Now, there is the interesting border case, right?
Okay.
And that's the case where alpha is equal to omega. And I've been saying omega, but it's really this omega naught, which is what we've called it.
Right.
Right? And in that case, look at these two equations. What happens to what's inside the square root?
Well, that goes away.
Yeah, that goes to 0, so that means S1 is equal to S2.
So my guess is, though, because the roots are the same in that case, my guess is, well, it's not really a guess, we obviously know this, but the solution, this solution form we've put up here won't suffice, and so we'll come back to that.
That's
right
right.
At the end. We'll come
So
back.
the critically damped case is kind of a little difficult to deal with, and I mean, we'll tell you in advance that we're just going to make you take some leaps of faith to figure out how that works.
We'll tell you what it is.
Yeah, but we're going to focus right now on the overdamped and underdamped cases. And as you would guess, the overdamped is easier to deal with because it's purely real. The underdamped, given that you already dealt with phasors, if you followed the order in which we've provided these modules to you, is not that hard to deal with either. So maybe you can start, Michel.
Okay, so let's start with the overdamped case. And what we're going to do in the following 3 slides is reproduce for you these terms we were just discussing. So here are the 2 roots, plus minus, the damping factor, and what we're calling omega 0, the resonant frequency. Okay? Now, we're going to get into what this omega naught is on the next slide in a very intuitive way, I think. But observe for the moment that the damping factor depends on the loss element and some combination of the energy storing elements. Whereas this thing we're calling the resonant frequency, this omega naught, depends only on the energy storing elements.
Makes sense.
Okay. Now in the overdamped case, it's very simple. Because alpha is greater than omega naught, as we discussed, these S's, S1 and S2, will just be negative real numbers.
Right.
So you have a combination of 2 decaying exponentials,
Aha.
A1 and A2.
I guess it's going to look like a decaying exponential of some sort.
Exactly right. And
Okay.
A1 and A2 can be solved for.
Okay. So let me look at this. So the voltage started, I mean, the numbers here just came out of some particular example, but the voltage started its initial value.
Call it Vs.
Yeah, call it Vs, and it just sort of decayed down, and it kept going, and if I'd gone long enough, it would have asymptoted to 0, because this is the natural response.
In the natural response.
Got
and
it.
if you recall, one of our boundary conditions was that A1 plus A2 equals Vs, and not surprisingly, when you put a 0 into
Yeah.
these, you get A1 plus A2 gives
Got
you
it.
the initial voltage.
Got it.
Okay. Now the underdamped response, I think, is a little more interesting.
Yeah, and of course you made me do it. All right, so let's set up the underdamped response. Again, we have the same set of equations that we had earlier, except in the underdamped case, we place the requirement that alpha is less than omega naught, right, if you remember that. Okay, so let's go ahead and now look at that. Now think about what this means. In the underdamped case, we said alpha is less than omega, which means this is a complex form.
Uh-huh.
And Euler's notation then allows us to write this as the sum of a cosine and a sine, and specifically what we end up getting, if you look at this complex form and the overall form of the equation, is you end up getting a oscillating behavior that dies out.
So I want to point out 2 things. One is something to point out to all of you at home, and the second is a sort of observation about the equation. But the first one is we played a little trick in the sense that we had a form which was A1 e to the S1t plus A2 e to the S2t in the previous, the general form. And when you substitute in these roots, in the case where these will have a j times whatever the magnitude of this is, if you do that, go ahead and substitute the whole thing, you should be able to convince yourself using Euler's that the resultant form looks like this. Okay, that's important.
Well, but that makes sense, right? Because if you have a real plus an imaginary in an exponential, you can pull out the real and leave it as an exponential, and that's the decaying part. And then the imaginary becomes the Euler's
Right,
representation.
you'll get 2 things that are imaginary, and together you'll see that they'll
Got
come
it.
down to this.
Mhm.
Now, the other thing is more interesting. The other thing is that both of the sinusoids will have a term in front of the t, which we'll call omega sub d, which is this here. Now you can see, of course, it's the second part of the root. But this is interesting because, think about it, it's omega 0 squared minus something. So basically, if we think this is something about a resonant frequency, which we haven't really talked about, the oscillation of the sinusoid is that shifted over by something that has to do with damping.
Oh, and that alpha was what we were discussing is related to the loss, because it had the resistor in the alpha term, which is my loss element. And so I think what we're going to see is, we will see, just looking at this mathematically, it decays, but it decays in an oscillating way.
Right.
And several things to note. So the decay, of course, represents the loss, right, of the exponential part.
E to the minus alpha.
Yeah,
t.
that's coming from the loss, so that's heat. But the oscillation is the energy storage elements shuttling energy back and forth between them.
Got it.
Okay? And remember, we're looking at the voltage across the capacitor. So as the voltage drops, it's shuttling it over to the inductor, and they're sort of shuttling energy back and forth.
Oh, and with each shuttling, so to speak, as current goes between them, they have to go through the resistor, and the
Because
resistor
there's
kills
current
a little
flow.
bit of it.
There's current flow, and the resistor is dissipating some of that energy as heat, and so it dies out. Now, think about our first order circuits. The resistor sort of affects how the energy is shuttled back and forth, and that is why it makes sense that the frequency of the oscillation will have a dependence on the loss as well.
So what you're also saying is that in the limit as there isn't any loss,
Yep.
there is no decay, so the amplitude of the sinusoid would stay constant.
Right.
This wouldn't be there, it would be a 1. And the frequency would essentially go to this natural resonant frequency.
Right. Now, we've been a little fast and loose with how we're dealing with this because this is time domain analysis, but you saw it before when we calculated the filter response using phasors.
I see.
Okay?
But the resultant seems to be that in the time domain, in the limit as damping goes away, this circuit likes to resonate at omega naught.
Right.
That's its sort of happy spot.
Exactly. And that is the identical behavior we get when we do the analysis with phasors.
Oh, that's right, because there's that resonant peak.
That-
Because it must be that that's where it likes to resonate.
That's right.
Well, I'm sure we'll come back to that because it's such an interesting idea. So, okay, that's pretty cool actually. It makes a lot of sense. And then of course, just to point out something Vec already said, with damping, these circuits do not resonate at 1 over square root of LC. Sometimes people will just say that. They'll look at an LCR and they'll be like, oh, that resonates at, or that oscillates at 1 over square root of LC. It actually oscillates at something near that, but it's depending on how much damping there is.
Right.
The more damping there is, the more you're sort of changing this frequency. Okay, now let's do the critical response. The critically damped response, we're going to cheat. And I'll tell you why. It's a very simple reason. First, let me restate or put on the screen exactly what we've looked at before, and then let me do the cheating. Now here's the cheating. When these are equal, this goes away, and both roots would be minus alpha.
Oh, I see the problem. Okay. Both roots are the same.
Right.
Okay.
And in fact, if you go back, you'll find that you can't get a complete solution with the form we've used before.
Got it.
So we debated with Vivek whether we'd sort of go through a slide on why it is that you adopt this form, and we felt that in the end it didn't really teach much. It was just interesting mathematics for those of us that like it. So I would say that do this in 2 steps. The first is sort of by dicta, we will tell you that in the case where it's critically damped, the previous solution doesn't quite work, and you have a slightly modified one, which is to say that there's only one decay, e to the minus alpha t, which you could expect because the root collapse.
Because the real part, yeah, okay, got it.
But you have to have 2 terms, one which is b1 e to the minus alpha t, and a second which is b2 t e to the minus alpha t. This t appears. Now, this is where we're going to basically just wave our hands, and that's to say that if you're really interested in how you arrive at this or what the intuition would be for a mathematician to have come up with this, there are a couple of different treatments you can find, mostly on the web. One is a time domain example of how you kind of go back and see that you should have a t. And the second that you can do with Laplace transforms for those of you that are interested in Laplace. But for the moment, just to get intuition about circuits, we're just going to tell you that this is the answer.
And by the way, to think about it intuitively, remember that these conditions were calculated from the voltage and from the derivative of the voltage. And that should give you a hint as to why you would expect to have a factor that has a t coming in there. Okay.
So we'll leave that alone for now. And all I want to do is show you the critically damped in comparison to the other two. Otherwise, the critically damped would just look like something decaying. And in fact, what happens is the critically damped case is the case right at the border. If you were to remove a little damping, it'll begin to wiggle to some extent. If you add more damping, you're just really clamping it down as a decaying exponential. It's that border case between the 2 types of behavior.
So it still looks, I mean, it doesn't have the oscillation behavior because there's no complex term.
That's right.
But it's just not exactly the same as the overdamped case. I mean, it's the specific boundary between those 2.
It's that exact boundary between right when this thing turns into having an actual sinusoidal condition.
Got it.
Okay.
Okay. Now everything we've looked at so far is, of course, the natural response because we turned off the forcing function, right?
That's right.
Okay. How about we then just pull this together very quickly by looking at how things would change if I went to the general form. Okay. And in the general solution, what I'm basically requiring is when I'm done, I'm not going to necessarily turn off the source voltage.
Oh, this is the case where, as we're solving for it, there's actually a source left in there.
Exactly. So when I'm figuring out what's going on after the transient, there's still some sort of forcing function in there. Okay? You can always deal with this conceptually by thinking about this as superposition. Okay? Because you will have your forcing function and you can figure out your natural response and put them together, right? Because the general response is essentially the more general case and the natural response is a subset of that.
Yeah, so I see. So you're going to get the total solution will be whatever the steady state is plus the transient.
Exactly. Okay?
We're going to go through this briefly because we've already done it in detail for the first order and the sort of analogies are all exact. So
right.
We're not going to go through it in huge detail.
So, you have the same equation as you had in the natural response, except
there's now the C term isn't 0.
The C is not 0, okay? And the reason for that is there is a forcing function in there, okay? And what that means is, A and B take the same form as they had earlier to a large degree, in fact exactly, except now C has this additional term in here.
Right.
Okay? And remember, look at this and think about what happened in the natural case. Vs was 0 in the natural case, which is why C went to 0.
Right. Okay. So what we decided to do with Vivek is, in the next slide, is show you just graphically what these look like. And then in the next module, we're going to do examples to kind of flesh this out. Rather than kind of regurgitate the same method all over again, except C isn't 0, we can, and because you've done first order, we're just going to show you this by way of example.
All right, so let's do it. Maybe, Michelle, you can do some of the examples.
Yeah.
The graphical behavior.
We'll just do graphical behavior. The examples we'll save for another module. But it's pretty straightforward intuitively to see what would happen when you close this. So here you're closing it. It's not allowed to decay to 0, but the final condition at infinity has to be that the voltage on this is Vs.
Aha, so now if I look at this, this is charging up the system, which means initially, because there was no voltage and it had been sitting there forever, it would start at 0 on the capacitor, and now it's going to charge up. Oh, I see the behavior. So depending on the values of L, R, and C, in other words, which set alpha and omega naught, I can see the underdamped, the critically damped, or the overdamped, but all of them are now shifting upwards.
Yeah, they're all going to this 24, which we've picked as our Vs.
Got it.
And it was 0 to begin with in this case. We didn't really define it properly. There should have been something that grounded. But we'll say that VC, the capacitor voltage, starts at 0. It's good enough. So it starts at 0 and wiggles up, or it critically damps up or overdamps up. And those things depend on alpha.
But why? Okay, so why don't we do a problem that's more like the ones we used to do earlier? Oh, yeah, like that, where we switch from one source to another source.
There you go.
Like that.
So here we start out at Vs. Right, and then we switch. This is the exact problem we did before, and here it'll decay to 0, right? Because does 0, and it's either going to do it by wiggling down. It's decaying, but it's got a wiggle, so it's an envelope that's an exponential, and then critically overdamped.
But if I were to put a second voltage source over here,
then you'd be going from a level, say, of 24 to, let's pretend the second one was 10. And you'd be wiggling down.
So it'll wiggle down to 10. Right. Got it. So the idea is basically the same as what we were doing in the first order circuits, and we're just putting it together.
Right.
Okay.
And here for your memory is basically what these things look like for a series RLC.
Okay, so it's good. So I can calculate the damping coefficients alpha and omega naught, alpha and the resonant frequency omega naught from those values, and that applies whether I'm doing the general response or the natural response. The main difference is what the final value ends up being.
Yeah, the boundary conditions give you, how these things work.
So maybe we can put that all together into a table. And we've looked at the two cases that, as Michelle indicated, are the most common ones we commonly deal with, which is the series RLC and the parallel RLC. And we've put the equations out here for you, okay? So these are the equations. We did our calculations for the series RLC, and so here's the equations from the series RLC. You can do the same thing for the parallel RLC and come up with your own set of equations, okay?
And in that case, by the way, the canonical way to do it is to solve for the inductor current.
Right, and you could, for example, you could get to it by KCL as opposed to a KVL in that case, right?
Exactly, yeah.
Okay, makes sense. So those are the equations. This is just for your reference. What we're going to do next is we'll take some specific examples, but we'll stop right now and we'll come back and pick up on that topic. See you later.
See you soon.